Okay, we're going to revise about electromagnetic induction. There are one, two, three, four, five, and six. There are six subtopic over here. Okay. One is magnetic flux, first magnetic flux, Faraday's law and Lenz's law, semiconductor, anistor in the inductor, and mutual inductance. Okay. Let's see the on the second page. Magnetic flux and magnetic linkage. Magnetic flux is a way to quantize a physical quantity of magnetic material. So magnetic flux is denoted by phi over here. So it's a phi is equal to B times A or B dot A cos theta equals to B A because it's a dot product. So B A cos theta. Okay, so it depends how much of the of the B that is flowing through an area. Okay, so the cos theta determines if a cos is 0, that means that it is perpendicular to the surface. You have the maximum of flux. Meanwhile, if the cos is 90 degrees, there are no flux going through it, and uh, cos 90, it will be 1. So if it's a max, cos 90 will be 0. It means that it is perpendicular. It is parallel to this to the plane. There will be the minimum of the magnetic flux. So the magnetic flux through the coil is maximum if the magnetic field is perpendicular to the surface of the coil, and 0 is parallel to the surface. Okay. The next page we have, for example, if we have a area of 50 centimeters squared, 500 turns in place in uniform magnetic fields. Okay, so over here we have 5.0 centimeters squared and 500 turns. It's a big turn over here, 500 turns. Okay, and the magnetic flux density means that the B of it should be straight now. The B that goes through will be a 0.50 Tesla. So calculate magnetic field linkage to the coil. We use the P equals to NBA cos theta, and cos will be 0 because it is perpendicular to the surface. Means perpendicular to the plane of the coil, and it will be 0.125 Weber. And calculate the change of magnetic flux linkage if the coil is rotated 90 degrees to the axis along the diameter coil. So from the plane is horizontal to us. We we, we rotated 30 degrees. So now the B will be still going up, and it's 30 degrees over here. So it will be 30 degrees to the the uh, the circular coil, and there you have NBA cos theta. It means that the final, this is the final, and this one will be the initial. Okay, so NBA cos 30 minus 1, so negative 0.167 Weber. A change is negative, it means that it is decreasing. Okay. Faraday's law and Lenz's law. For Faraday's law, it says that whenever there's a change in magnetic flux linkage through a coil or solenoid, an EMF will be induced in the coil and solenoid. And this effect is known as electromagnetic induction. So over here, we have a area of a magnetic field, and then we stretch the coil. Okay. The coil is decreased because A is decreased. So when you stretch it, the area of the coil will be decreased, so there will be an electromagnetic induction through the coil. Okay. it depends on the it says that is it okay. So Faraday says that the magnitude of induced EMF in the coil in the situation just now is directly perpendicular to the rate change of magnetic flux linkage to the coil. So E equals to the change of the flux divided by the time, and negative sign equation is a result of the Lenz's law. Okay. So Lenz's law says that induced current will always flow in the direction as to oppose the change of magnetic flux causing it. Okay. Any induced electromagnetic force will be direction such as magnetic flux create will oppose the change of flux produced. In simple terms, induced current tends to maintain original flux through the circuit. So Lenz's law is a consequence of principal conservation of energy as explained to the following example. Okay, so there is a magnetic field that is going to a loop, and what happened is it will be because it came from far and goes towards the near of the circular coil, it means that it will be increasing the B. Okay, what happened? The nature will be oppose the increasing B by putting down in opposite direction. So B oppose. Okay, so they will be opposed at putting downwards. And if you use right hand rule, it shows that the current use your thumb pointing down, and the current will be flowing if you are viewing in the top. I mean, if our eye is on the top, we see that the current will be flowing in the clockwise direction. Okay, from the top, it will be in clockwise direction. Meanwhile, in the second situation, if the magnetic field line is decreasing, okay, because we are pulling back the magnetic bar, the magnet bar, and what happens is nature does not want it to happen. There will be B pointing up, opposed, that is pointing up. So it will be the direction of the induced current. So you put your thumb going up, right hand rule, and you see that from the top, if you're viewing on the top, so you can see that the from the top you can see that it is counterclockwise direction over here. Okay. So if there are no movement, for instance, this is no movement, there will be zero EMF. One thing about Faraday's law, you see that Faraday's law, it says that Faraday's law is talking about induced EMF. So Faraday's law, you have to pair with induced EMF. Okay. Meanwhile, the Lenz's law is talking about induced current. Induced current. Both of them are different. Induced EMF and induced current is actually a different thing. Okay. So if you write the statement of Faraday's law, you have to include induced EMF. Okay. Is such as it's in a coil that is proportional to change of magnetic flux linkage to the coil. But when you define Lenz's law, you have to include induced current. It is not induced EMF. Students tends to take granted about this. Okay, induced current will always flow in the direction so as to oppose the change of magnetic flux which causing it. Okay, so this is what happen when you have induced current and induced EMF. Okay, I already explained what happen when you increase and decrease the magnetic field throughout the circular coil. So example over here, circular coil radius 50 centimeter with 400 turns, and resistance 10 ohm is placed perpendicular to a uniform magnetic field as shown diagram below. If the magnetic field reduces to 0 in 0.4 second, so it came from 5.0 times 10 power negative 2 Tesla turns into 0 in 0.4 second, 0.0 second. Determine the average induced current in the coil using the Faraday's law. E equals to negative d flux over dt. So final flux is 0 and initial flux is NBA because it is perpendicular. So because 0, so it will be the maximum divided by T, NBA divided by T. So 400 times everything, you have 39.27 volt. V equals IR or E equals to IR, magnetic EMF equals to IR. So 39.27 equals to IR, that's R is 10. So current that flows through over here is 3.927 ampere. The direction of induced current in the coil. So if we take the picture in another view, we take the coil in that view. It seems that first it was pointing, the B is pointing downwards. Okay. If you are watching it from the viewing it from the top view, B is pointing downwards, and suddenly it's reduced to 0. It means that the B is decreasing. B is decreasing. Okay, decreasing. So there will be B that oppose the decreasing. Okay, so you actually you pulling down, or you pulling up this red B, so it will be B opposing the decreasing. So B is pointing downwards. So you use the right hand rule. Is use your right hand rule grip. You pointing with the thumb pointing downwards. You have, you can see that it is actually in the how to say, clockwise direction. Okay, so the induced current will flow in the clockwise direction because B is increasing and B of the induced is opposing it. The heat dissipated in the coil. Okay, the dissipated coil W equals to EIT. Okay. So we have the EMF V IT. 39.27 times 39.27 and 0.04. So the heat will be 61.7 joule. Next part, if we have a moving conductor moving a magnetic field. For this one, okay, sometimes it's very tricky to explain this thing. Okay, so if you have a rod that is inside a region, okay, as you push, okay, is moving in uniform magnetic field, acting the phase with constant velocity v. When you have a constant velocity, actually there are no acceleration. Okay, so there is no F. The electron will in rod will explain the magnetic force FB towards the bottom of the rod as shown in figure B. So when we pull to the right side, okay, there will be a force of magnetic field towards downwards. Okay, which one you use, left or right? You use FBI, FBI, FBI. Okay, you use right hand rule. Okay, for induce. I. Okay, for this is what, electron. Okay, for electron, we are using right hand rule because left is for proton, right hand for electron. So using right hand rule, you can see that F is pointing downwards. B is pointing to the page, and V is your middle finger is pointing to the V. So of course F is pointing downwards. Okay, as a result, more and more electron will be accumulated at the bottom of the rod, and upper end will be induced positive charge. So here will be negative, 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 negative. Over here will be positive, 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 positive. Okay. So electric field will be set up across the rod. Electron will experience upward electrostatic force. So as you see that when we have positive, negative charge on top and the bottom of this area, there will be electric field E over here from the top to the bottom. Okay, from the top to the bottom. So electric field will be set up across the rod, and electron will experience an upward electrostatic force. Okay, so the current, the electron goes upwards with electric force. So when we have equilibrium, FV equals to FE. Okay. I mean that when the electron does not goes up or down, it means it was static in the middle. FV will be equal to FE BeV. This is force by magnetic field. EE is force by electric field. BeV equals to E over L. E over here is MF, EMF divided by the L. So E will be BLV. You cancel EE, and then you have E equals to BLV. So EMF is, the induced EMF will be B times L times with the V. If the resistor of resistance R is connected across the conductor, and induced current will flow as shown below. So after we move the rod inside the magnetic field, and then we put a resistor down in the middle. Okay, so there will be B induced in the left side, and V is pointing outside. So there will be current that flows in the counterclockwise direction. So you see that I is pointing this way. Okay. How you determine which one positive, negative? You refer back to where is a positive charge and where is a negative charge. Positive charge over here, negative charge on downwards. You can see that in the diagram, positive on top, negative at the bottom. So the current will flow through a counterclockwise line. Okay. But as I said, V must be constant, so there are no acceleration of force, other kind of forces that acting through the system. The rate of heat dissipated of resistor is P equals to I squared V. It's the same thing. Yeah, page number 7. And P equals to B squared L squared V squared over R. It's proven that Lenz's law is result of conservation of energy. When current flowing into the conductor, a magnetic force F will act on the conductor in a direction against the motion. Thus, mechanical force of the same magnitude must be applied in forward direction to move the rod with constant speed. So mechanical power supplied by the force is given by P Fv. So B squared L squared over R. From the equation above, we can conclude that mechanical power supplied is equal to the rate heat dissipated of the resistor. Okay. So how much is supplied? How much you move the rod will be equal to rate how much the heat dissipated by the resistor. Induced EMF in the plane coil. Okay. This is a basic components of a dynamo. Okay. When you have a magnetic field in between, and you turns the coil, okay, you will generating the induced EMF or induced current. So from Faraday's law, I mean from the formula of magnetic flux equals to B N cos omega t, and Faraday's law E equals to D flux over dt equals to B N omega sine omega t. Okay, because why we have omega? Because the thing is rotates, so we have omega. So EMF will be increase and decrease and increase and decrease. So E naught, I mean the peak of the EMF, E naught equals to BAN omega. Okay. So for example, over here, amateur 60 Hertz AC generator rotates in 0.15 Tesla magnetic field. If the area of the coil is 2.0 times 10 power negative 2 meters squared, how many loops must the coil contain if the peak output voltage is 170 volts? So we take about from the formula E naught equals to P N omega. So omega is 2 pi f 170, and then you want to find how much N. N will be 150 loops of coil needed to peak output 170 volt. Okay, so this is actually peak output. It's not the RMS of the voltage. Self-induction is considered of coil consisting N turns and carrying current in the counterclockwise direction, as shown diagram below. Where's the diagram? Oh, next page. However, suppose the I change of the kind, according to Faraday's law, EMF will be induced to oppose the change. EMF generated is self-induced EMF and back EMF, which we denote as EB and EB, back EMF. A new thing for you. Back EMF, when the current through coil is changing and EMF will be induced in the coil. This known as the self-inductance. So what happens is when we switch on, there will be increasing B, and there, because of the length and Faraday's law, there will be B that is opposing the increasing. Okay, then I put as arrow pointing outwards, oppose the increasing. So that when you switch on, there will be opposing of the current that is flowing. So that we have a current with a gradient like this. It should be like if it's like this one, but it will be slower than before. When the switch is closed, the current coil arises as shown in the graph. The rising current across the changing flux induced back EMF. So the back EMF is opposing the EMF produced by the that is running through the inductor. On the left side, the induced EMF opposes the riding current. So E back equals to negative L di over dt. So L is a constant for the inductor. Self-inductance as a unit is in Henry. So relationship between self-inductance and magnetic flux linkage. So E equals to D flux over T, EB equals to E. So, or we can say that negative L di over T equals to D flux over T. So L is actually flux divided by current. Okay. Energy stored in inductor. Inductor can store energy in the form of magnetic field. So energy stored in the inductor is 1 over 2 Li squared. So there are two things over here. Remember, if inductor, it will be 1 over 2 Li squared. For capacitor, energy is stored through in the form of of electric field is 1 over 2 CV squared. So you can see that the similarities between them. If current is interrupted spark, mechanical energy is dissipated, self-inductance can be a problem where the breaking of circuit can large EMF. Okay, so calculate energy stored in the coil with the same reluctance L is given 1.25 millihenry, and the current through is 0.5 ampere. So energy stored, you just use the formula given, that is 0.31 times 10 power negative 3 joule. If you have a long solenoid, okay, the B will be BU and I. This is, we have derived before, BU and I. U equals to U N over Li. So the magnetic flux linkage through the core will be L U naught. Okay, remember you are using U naught, not E naught. Okay, U naught because you are dealing with B, not E. U naught N squared pi R squared divided by L. Mutual induction when we have two coils are placed on each other. Okay, changing current, one coil induce EMF to another coil. This effect is called mutual induction. It must be near one of the. This is basic principle of wireless charging. The second coil direct information the rate change of the first coil. So E2 and E1, both of them actually has the same formula. Negative M di over dt, negative M di over dt. Okay, so both of them has the same mutual induction. Mutual induction between two long coaxial solenoid. Okay, one is core inside, one is in outside, outer core and inner core. If you're using this kind of arrangement, we are going to obtain. Okay, we're going to use, again, we are using Faraday's law, E equals to d flux over dt, E1, E d flux over di 2 over dt. Then we have M equals to U naught N1 N2 pi R squared IL. Okay, U naught N1 N2, it depends on the U naught, no, it depends on the number of loops on the first turns, and second turns pi R, and the radius of the R1, it means that the radius of the first diameter, the core, and outer core, how much the radius of the outer core, and times it with the L. For example, over here, a long solenoid has n turns, length L, cross sectional area A. A short core with the n turns, it works around the middle of the long solenoid. Explain the phenomenon of mutual induction. This is changing current. One coil causes a magnetic flux linkage in the neighboring coil. As a result, an EMF is induced in the neighboring coil. Okay. Derive expression for mutual induction in terms of A and TL. This mutual induction is do you need to remember how to derive? Oh, you have to derive. So under mutual induction, you have to derive expression for mutual induction, meaning two coaxial solenoid at the same cross-sectional area. Yes, you have to learn how to derive it. Okay. Then you have M equals to U naught N1 N2 A over L. Example, Faraday's law and Lenz's law. So I say Faraday's law, you have to pair with induced EMF. Lenz's law, you have to pair with induced current. And one over here, I think you can read by yourself. Determine the initial flux linkage to the coil and derive the induced EMF in the coil at the time t. Okay, let's take metal loop. And this is, sometimes they just change the area. Sometimes they change the flux. Both of them, no, change the B, and both of them contribute the changing of the flux. Okay. So any question? Abby, Sheridan, and Kishika, any question?
Sir, the induction, sir, I don't understand properly, sir.
Which one?
mutual induction, the two solenoid.
Of the two
Solenoid
solenoid
inside the. Yes.
inside. Okay.
Yes, sir.
Which part you don't understand?
We must determine the. We must determine the B. How to determine the B, sir?
The B?
Yeah.
Where it doesn't say. Usually it doesn't give you the B. It gives you the flux directly. The number how
Okay.
much the flux. You see that you can in this example. Okay, it doesn't mention any B.
Yes, sir.
Usually they mention how much the flux or how much the I. Okay.
Okay. Yes, sir.
Any more question? Sheridan, Kashika?
No, sir.
Any question, Kashika? Any problem with induction?
No, sir.
Okay. Abishai, if you want the B, you also can use B because you know NI over L this one. Okay.
Okay. Okay. And so for induction, right, sir? Mutual induction. Do we need to find the direction, sir? Do we use Fleming right hand rule, sir?
You mean the where is the north and which one is the south?
Yeah. Do we need to use, sir?
It can be asked because actually north and south has been mentioned in Form 5. Let's say you have a coil over here for this one, left and right. So this one increasing. So what happened to the coil?
Yeah.
What will be the pole of this side and how much is the pole of this side?
Okay.
So if it's increasing, what will be the pole over here? When it was decreasing, what will be the pole over here? Yes, it can be asked.
So, but at this time, they will ask in section B, right, sir? Because last year, SEM 2, they asked in section C, induction.
Who knows? I don't know. Who knows?
Yeah.
Yeah.
Suddenly they ask again. Yeah.
Okay, I think we can stop here. I will, because you were late, I already started the recording. I will put on the YouTube.
Okay, sir. Thanks, sir.
Okay, see you again.
Thank you, sir.
Sorry, sir, late.